Good afternoon, everybody. Welcome to another Heidelberg Joint Astronomical Colloquium. This is the real hot place to be in Heidelberg today, despite all the other events going on. And we're very, very happy to welcome today Mark Wolfire. Last week, you may remember, we were looking at dark matter. Now we're going back to the visible baryons, and there's literally no better person to tell us about that than Mark. I'll invite Melanie to introduce Mark fully.
Thank you. So yes, it is a pleasure to welcome Mark here in Heidelberg from University of Maryland. Mark did his PhD in 1985 at the University of Wisconsin on the conditions for the formation of massive stars. Then he moved to several places, including NASA Ames, CFA, and in 1996, he moved to University of Maryland, where he has been since then. And since last year, you're now emeritus there.
Right, correct.
So Martin is an expert in galactic and extragalactic photodissociation regions, so PDRs. He has developed models to predict infrared and sub-millimeter lines from many telescopes, so Herschel, Sophia, ALMA, and now they're used for JWST observations to use these observations as diagnostics for the gas physical conditions. So Mark is also a co-developer of the PDR toolbox, which is an open source tool to derive the physical conditions of PDRs from observations. And today is not only going to talk about PDRs, but also all about cars and stars. So please, Mark, take it away.
Thank you. Thank you. So this talk is on photodissociation regions, or PDRs, or a talk that I like to call Stars, Cars, and PDRs. But first, I'd like to thank some funding agencies here, but especially the local centers and the institutes for the opportunity to present this Heidelberg Joint Astronomical Colloquium. Stars, Cars, and PDRs. So first, I'll start off with a brief introduction to PDRs. What are they? Where are they found? Some general characteristics, and how are they related to stars? Then we'll look at the basic structure and chemistry of a PDR. We'll look at the dominant heating and cooling processes, the gas line diagnostics and where they're found, what you can learn from them, and how are they related to cars. And then we'll look at PDR models and observations. We'll look at some applications in the diffuse gas, the Orion Nebula complex, and also the Orion bar. Okay, so what is a PDR? PDR is a photodissociation region. A working definition is a PDR is a gas phase in which the UV radiation plays a role in the heating and the chemistry. The UV range that I'm talking about is responsible for heating the gas and dissociating molecules. The upper end here is 13.6 EVs. That's the hydrogen ionization edge. So these are hydrogen neutral regions. And the UV field is usually measured in units of the interstellar field. So a G0 of 1 is the interstellar field. And G0 is usually taken to mean the Hobbying field. There's other measures of the interstellar field. There's the Mathis field and the Drain field. They're all within a factor of 2 of each other. So the energy flux in a Hobbying field is 1.6 times 10 to the minus 3 ergs per centimeter squared per second, and a photon flux of about 10 to the 8th. And then fields that we typically encounter range between 1 for the interstellar field and 10 to the 5 for the field directly behind the stars powering the Orion Nebula. So then where did we find these things? Well, one place is where bright O and B stars shine on molecular clouds. So around the O and B stars, there's a H+ region and H2 region. And then the UV radiation that escapes that H2 region illuminates the molecular cloud and produces the PDR. And sometimes this is called the classic PDR. So at the outer edge, you've got C+ H1 gas. A little bit deeper in, you have C+ H2. This is the so-called dark molecular gas because it doesn't emit brightly in CO. And then deeper in, you've got the rest of the molecular cloud, which is mainly H2. And then using this definition, most of this H2 gas is in a PDR. You also find PDRs in the diffuse gas. This is a cold atomic cloud of temperature 80 degrees, a warm atomic cloud of temperature 8,000 degrees. This is called the cold neutral medium. This is called the warm neutral medium. And these are also illuminated by the interstellar field. So these are also PDRs, but there the column densities are lower, the UV fields are lower, and the densities are lower than what you find in one of these classic PDRs. If you look at the ISM as a whole, most of the non-stellar baryons in our galaxy and in other galaxies are in PDRs. So another place you find PDRs are in early stages of star formation, where the protostar is still enveloped by its natal molecular cloud. You find PDRs in protostellar disks and outflows. There, the column densities are much larger and the densities are much larger than you find in the classic PDRs. And you also find PDRs in later stages of evolution, where the winds have created these shells that are also illuminated by UV radiation. Now, this background image is the Orion bar that's taken with the James Webb Space Telescope, and we'll come back to that image a little bit later. So here's a schematic of a PDR as a function of distance into the cloud. At the outer, well, this is a function of distance, or AV, or column density, where the relation between column density and AV is the hydrogen column is AV times 2 times 10 to the 21. So here at 1, that's a column of 2 times 10 to the 21, and at 10, that's a column of 2 times 10 to the 22. So then at the very outer edge, you have a source of UV radiation and also ionizing radiation that could come from OB stars or the interstellar field. And then before you even get to the PDR, there's this H2 region of ionized hydrogen with a temperature of about 10,000 degrees. And that emits in hydrogen and helium recombination lines. There's a bunch of fine structure lines in metals that are excited by electrons. And there's optical recombination lines that you see from metals. Then deeper in, right at the surface of the PDR, you see neutral hydrogen, neutral helium, C+, and neutral oxygen. The heating is mainly grain photoelectric heating, and it's cooled by C+ and O1 fine structure line cooling. There's also fine structure lines for metals, and these are excited by electrons and also collisions with neutral hydrogen. And there's a very strong dust continuum emission, and there's poly emission, these broad band emission from large molecules. The temperatures you get are typically 100 to 1,000 degrees. You could get larger temperatures or lower temperatures depending on the ratio of the UV field over density. Then deeper in, H2 forms on dust grains, but the UV opacity, UV field is lower due to dust opacity. And so the H2 is no longer dissociated, and you get a conversion between atomic hydrogen and molecular hydrogen. You still have grain photoelectric heating. You also have C+ recombining with electrons to neutral carbon. So you start to see lines again from C+ and O1, but now you see C1 lines. And you also start to see rotational and vibrational emission from H2 and other molecules. Then CO forms. You see the high J CO lines, and deeper in, you see low J CO lines. You can also get ice forming on grain mantles. The heating is mainly cosmic ray heating. You can also get some heating from infrared radiation that's produced over here and then penetrates deeper into the cloud, and you get CO. Temperatures are typically 10 to 100 degrees. And this transition here between H+ and H is called the ionization front. The transition between H and H2 is the dissociation front. And then these other transitions are also functions of G0 over N. If there's a high ratio of G0 over N, those transitions can be pushed deeper into the cloud. For a low ratio of G0 over N, for like a high density clump, these transitions can move to the surface, and they can sometimes get quite close. So PDRs are also the region where stellar feedback processes interact with the cloud, the PDR and the molecular cloud. And typical processes that we talk about are photoionization and photodissociation. So photodissociation is where the UV field dissociates the molecules into ions, into atoms. Photoionization is where the ionizing photons can then ionize those atoms. There's photoevaporation. That's where the UV field and the ionizing photons heat the gas. And if the sound speed is large enough, larger than the gravitational attraction of the cloud, then those molecules and atoms can escape. There's stellar winds. So for stellar winds, down here, there's a shock from the wind that produces very hot X-ray emitting gas, and that can expand, push on the PDR and push on the cloud. There's thermal, H2 region thermal expansion. So this is 10,000 degree gas here that can also push on the cloud. And then radiation pressure and supernova, although I think most people will agree that these are of lesser importance, but for radiation pressure, the momentum in stellar photons interacts with dust grains. The dust grains push on the gas, so that can help to disperse the cloud. And then supernovas is a blast wave that can help to disrupt the cloud. And we're going to look at some of these a little bit later. So let's look at this grain photoelectric heating process in a little more detail. So along comes a photon. It's absorbed by a dust grain, and it ejects a hot electron that goes off and hits hydrogen or helium. And that's what basically heats the gas. But that electron kinetic energy is a function of the grain charge, because it has to overcome the Coulomb barrier of all the accumulated charges on the grain. So you can get the grain charge by balancing photoionization with recombination. The photoionization rate is proportional to the photon field, G0. The recombination rate is proportional to the gas electron density over 2 to the 1/2. So photoionizations over recombinations are proportional to G0, 2 to the 1/2 over NE. You define epsilon to be the energy that goes into gas heating divided by the absorbed UV photon energy. So that's a measure of the photoelectric heating efficiency. And so epsilon is a function of G0, 2 to the 1/2 over NE, or the photoionization over the recombination rate. So Bakes and Thielens, Weingartner and Drain, recently Bernet, calculated this heating efficiency for jumbo 0.25 micron grains, all the way down to 5 angstrom particles, which are really large molecules. And they get this heating efficiency. This is heating efficiency as a function of G0, 2 to the 1/2 over NE, or the ionization over recombination rate. So when the ionization rate is small, you get a high heating efficiency of about 5%. When the ionization rate is high, grains get positively charged, and that heating efficiency drops off. They also found that half the heating comes from the smallest grain sizes, really large molecules, or PAHs, polycyclic aromatic hydrocarbons. And this is for 2 main reasons. First, the yield increases as the grain size decreases. So the yield is the fraction of electrons that get to a grain surface that can then be ejected and heat the gas. For a large grain, the electron kind of rattles around inside, and that energy is lost to infrared continuum radiation. But for a small grain, there's a greater chance that that electron will get to the surface, which can then be ejected. The other reason that these small grains, small particles dominate is because the ionization over recombination rate goes as grain size squared. So small grains are neutral, they have a high efficiency. Large grains get charged up and their efficiency drops. So then you can write down the photoelectric heating rate as a constant, the density of hydrogen nuclei, this efficiency times the radiation field. So PAHs are important. They dominate the photoelectric heating. They govern the electron fraction in the gas. They may also be sites of H2 formation. In one of the early papers, which suggested that PAHs were the carrier of these observed infrared emission bands, was this paper, Polycyclic Aromatic Hydrocarbons and the Unidentified Infrared Emission Bands Auto-Exhaust Along the Milky Way, in which they compared this observed infrared spectrum with the infrared spectrum of auto-exhaust. So they found that PAHs dominate the grain photoelectric heating by converting stellar photons to heat via this grain photoelectric effect, and PAHs have an infrared spectrum that looks like auto-exhaust, hence stars, cars, and PDRs. This is a schematic of how you would calculate a typical PDR model. You start at the outer boundary and you step in AV and you iterate around on three major processes. So first you write down all the equations for the formation and destruction of species, and you find the abundances for which formation equals destruction. You find the gas temperature for which heating equals cooling, and there's usually some transfer or transfer approximation so that you know the local UV dissociating radiation field. But now these processes in blue are all interconnected by additional processes. So say you want to get the thermal balance gas temperature, you need to know all the abundances, but to know the abundances, you need to know the temperature that drive the reactions. Or if you want to know the photo rates that go into the chemical balance, you need to know the local radiation field, but those are related by the line opacities and the column densities. So for every step, you need to iterate around on all of these processes until you're converged. Then you get the local abundances, the local gas temperatures, the local volume emissivities, and you do that for every step until you get to the edge of the cloud. And then you finally know the run of abundances, the run of gas temperatures, and the emergent line intensities. Now, there's several groups working on PDR codes. This is ours. This was based on the original Thielens and Hollenbach code. There's many updates along the way. There's the Meudon code with a detailed description given by Frank Lapetit in 2006, plus many updates. There's the Cosmetau code with a very recent detailed description. The Cloudy code, which was originally just for H2 regions, but has also been extended into the PDR gas. There's the University College of London PDR code, and the warp field code, which takes cloudy and then combines it with a 1D hydrodynamic code. Now, most of these codes are plane parallel or 1D spherical. Mine is a strictly plane parallel code. But for example, Cosmetau can do spherical geometry, and the UCL PDR code has been adopted for 3D geometry and is used in hydrodynamic simulations. So let's look at some applications and some observations. I said that the diagnostic lines come from different places in the PDR. The lines have different heights above ground, different energies above ground. They have different critical densities. So you can combine those diagnostic lines to try to learn something about the physical conditions in the PDR. So here's an example for RCW 49. This is a massive star forming region. Carbon-2 is in red. The green here is the pi emission, and it's pretty faint, but there's also blue dust continuum emission. And then we can take observations of the carbon-2, the CO, the infrared continuum, and the 63 micron line, and combine them in various ways and feed them into our PDR toolbox. So the toolbox has grids of PDR models. They have our models plus Cosmetau models. And then you can use that to constrain the incident radiation field, and the model density. You can also use, try to find the model thermal pressure if you have grids of constant thermal pressure models. But in this case, we find a best fit for all these lines at about a UV field of 10 to the 3, a density of about 3 times 10 to the 3, and a gas temperature from the model of 250 degrees. So using this, we found the physical conditions in this shell. And we found the thermal pressure in this shell. So this is an example for just a single fit, a single position, but we can also make UV field and density maps from observations from line maps. So this is an example from the reflection nebula NGC 1333 from Knight et al. You get a maximum UV field of about 3,400 and a density of about 2.5 times 10 to the 4. And so in this paper, we used the UV field and the density and the temperature to try to make maps of that charging parameter, P0, T to the 1/2 over NE, and compare it to PA features. So to see how those PA features change with the charge. Now, if you go to the PDR toolbox, you'll find Jupyter notebooks and Python scripts, and you'll see how to make all of these figures and how to make these fits. And all of this was done by Mark Pound. So what I did was I made the model grids that go into the fits, but all the rest really was done by Mark Pound. So let's look at a different example. This is PDRs in diffuse gas to try to measure the cosmic ray ionization rate in the diffuse gas. And this is the diffuse gas chemistry made by Van Dishoek and Black. So in mainly atomic gas, you start off with a cosmic ray ionization of hydrogen to H+. Then with charge exchange with oxygen, you get to O+. Then with H2, you get to OH+. And then with H2, you get to H2O+. In mainly molecular gas, you go this way around. You start with a cosmic ray ionization of H2 to H2+, then to H2 with H3+, and then with oxygen to OH+. Now the OH+ can either undergo a dissociative recombination, which breaks it back into oxygen and hydrogen, or combine with H2 to get to H2O+. If you work out all the dependencies, you'll find the fractional abundance of OH+ and H2O+ are proportional to the cosmic ray rate over the density. So the thing to note, though, is that the oxygen is not ionized by UV radiation, nor is H2. So the OH+ and H2O+ formation must be initiated by a cosmic ray. Now, there's been surveys by Herschel and Sophia of the H2O+ and OH+ in absorption in the plane of the galaxy towards background infrared sources. So you see in the plane of the galaxy, these absorption features that are from diffuse clouds along the line of sight. But they get spread out in velocity due to the rotation of the galaxy. Now, Indriolo published a list of 100 column densities from various species along various lines of sight. And we made a model grid for clouds of different total AVs. So this starts at 0.03 and goes to 3 in red. And the ratio of cosmic ray ionization rate over density, where this is normalized to a density of 50 and an ionization rate of 10 to the minus 16. And then this is overlaid on observables. So that's the OH column over the hydrogen column versus the OH+ column over the H2O+ column. So as you go for clouds towards larger AV, you get a higher molecular fraction in the cloud, and you convert more of that OH+ to H2O+, so you get to lower ratios. Then as you increase the ionization rate, you increase the OH+ abundance, so you get higher ratios. So we take our grid and we overlaid the observations and we find the mean cosmic ray ionization rate of 2.9 times 10 to the minus 16, and that's for a density of 50. So that's the way things were a couple of years ago. And then our collaborators here at the Max Planck Institute for Nuclear Physics measured the OH plus dissociative recombination rate using the cryogenic storage ring. So what that gets you is you can measure the rate at cold temperatures that you would actually find in the diffuse gas, and you get a very cold molecule. So the molecule is not excited. And that gives you the rate shown in blue. The rate we were using is here in orange. This is the Mitchell rate. So that is also an experimental rate, but it was a rate for an excited molecule. And so they get a factor of 5 higher dissociative recombination rates than what we were using. So if the DR rate is higher, the abundance is going to be lower. So you need a higher cosmic ray rate to make up for that difference. So then here's our new grid using the CSR rate. And we now find an ionization rate of 6.6 times 10 to the minus 16. So this is 2.3 times higher rate than we had with our previous results. So this is an example of using PDR models, observations in the galactic plane, and a very recent laboratory measurement to try to estimate the cosmic ray rate. And I can also say that we do plan to measure, or they plan to measure, the H2O plus dissociative recombination rate. I also understand the H2D plus rate has been measured. So we're looking forward to taking a look at those new rates and see how that might change the cosmic ray rate. So here's an example of a classical PDR. So this is where the O and B stars shine on bright molecular clouds. This is looking at the Orion Nebula complex. So that's down here. There's M42, M43, and NGC 1977. And I think it's fun to see how your stars look in relation to naked eye stars. This is the Orion constellation that even a theoretician can find. Those are the belt stars there. Down here are the, I think it's those are the knees. And then the shoulders are up here above the plot. And then this is sometimes called the sword region. So this is then a blow up of the sword. There's H alpha, the carbon-2 line, and the CO. So H alpha is the ionized gas. The carbon-2 is the neutral PDR gas. And the CO is the molecular gas. There's some data that's missing up here. But you can see this bright ridge of CO. That's where the stars form. You can see the carbon-2 has these rings here and there. And then the H alpha, the ionized gas, seems to fill in these rings. And then down here below is an expanded view of the carbon-2. So this was a map taken by the Sophia upgrade instrument. This is about a 1 degree by 1 degree field of view. And again, we see these rings. This is the M42 ring, sometimes called the Veil shell. There's M43 and NGC 1977. So we have the rings of emission, but are they really rings or are they expanding bubbles? So one way to tell is to look at the velocity resolved line profiles. And this entire map has 0.2 kilometers per second resolution. So we can make a cut right across the bottom of this bubble here, and then look at the line profiles. If we start right at the edge, most of the velocities are in the plane of the sky. So we see the background emission here at about 8 kilometers per second, and the shell is pretty close to the background. But then as we move across this cut towards the center, the shell becomes more and more blue shifted. So that's coming towards us until you get at the center of the bubble that has a maximum blue shifted shift of 13 kilometers per second with respect to the background. And then as you keep moving across this cut, the emission is faint, but it moves back towards the background. So this is just what you would expect for an expanding bubble. So it's not just a ring of emission, but it really is an expanding bubble at 13 kilometers per second moving towards us. So here's the picture that emerges. Here is the entire M42 region. It's powered by this set of stars here called the trapezium with theta 1 OREC dominating. It shines on this background cloud. This is the Orion molecular cloud. We see neutral gas photoevaporating off the surface of this background cloud at about 1 kilometers per second. There's a strong wind from theta 1 OREC that goes out, it gets shocked and produces 10 to the 6 million degree gas, X-ray emitting gas. So most of this is filled with X-ray emitting gas. Then there's this H2 region at the edge. It kind of gets squished up against the neutral PDR gas. This is the neutral veil shell here, and that's expanding towards us at 13 kilometers per second. Now you can measure the mass of this shell. One way to do that is by getting it from the dust emission. And this is a pretty typical way to do it. What you do is you fit the dust temperature to the energy distribution. Then you get the column density of dust by measuring an intensity at a wavelength. And you have to assume some gas to dust mass ratio, typically 100. And so from that, you get the mass of this neutral shell. We measure the expansion velocity from the carbon-2, so that gives you the kinetic energy of this expanded shell. And you can try to compare that kinetic energy with other processes that might be powering the expansion. So here's M42. You get a mass of 1,500, velocity of 13 kilometers per second, kinetic energy of 2.5 times 10 to the 48. Now, if you look at the luminosity in the wind and you multiply by the time of expansion, you can estimate the integrated energy in the wind. And you can compare that to the kinetic energy and you get a number which is comparable. Now there's other ways to lose that energy in the wind, but at least these two numbers are pretty close. Now, if you look at M43 and NGC 1977, these are powered by early B stars. The wind luminosity is much lower than for M42. So the kinetic energy here is 40 and 50 times bigger than the integrated wind luminosity. So what else could be powering these winds? Well, in M43, you can look at the thermal pressure in the H2 region compared to the PDR, and in NGC 1977, you can look at the thermal pressure compared to the PDR. And even if there was magnetic and turbulent pressure contributing to the PDR, it looks like the H2 region thermal pressure still dominates. So at least in this paper, the PAPS papers, we find that the M42 bubble may be powered by the stellar wind. M43 and NGC 1977 might be powered by thermal expansion. For RCW 49, which we looked at earlier, we also find that stellar winds dominate. But this notion of a stellar wind-driven bubble is really somewhat controversial. There are some hydrodynamic simulations that suggest that turbulent mixing at this H2 region boundary mixes in colder gas into the X-ray bubble, and so that would reduce the effects of the X-ray bubble. But Chavance et al. Find that stellar winds or photoevaporation in nearby galaxies have the shortest timescales for cloud disruption. So these are sort of complementary results. You know, we're both suggesting that stellar winds might be important. This is photoevaporation, and here I've talked about thermal expansion, but they're similar in that the stellar ionizing photons ionize the gas and heat the gas, and that's really the basic process of what's going on. So in this case, we've tried to use the kinematic information in PDR lines to learn something about the dominant stellar feedback process. So now let's look at a close-up of the Orion bar. with JWST. Let me go back. So here, this little image down here, this is the trapezium is up here, and it's hard to see, but there's a little white line that goes across here. That is the Orion bar, and that's what we're going to look at in JWST. So this is a near cam image. The trapezium is way up here. That's powering this PDR. And the scale here, this bar is 10 arc seconds, which is about 0.02 parsecs. But the resolution in these images is about 0.1 arc seconds to 1 arc second. So the spatial resolution in these images is just really quite astonishing. You can see very small scale structure. The blue here is the ionized gas. The red is the PA emission. And the green is UV pumped H2 and also dust emission. So you see the ionized gas up here. There's the ionization front. Then there's the PA emission. The PA emission comes up in red here. And there, if we had the carbon-2 and the O1 overlaid, they would also come up where the PA emission is. Now we've taken a cut in near spec, nearly perpendicular to the bar. And we see that below. Here's the bracket gamma. So that's the ionized gas that peaks up right at the ionization front. This cut passes through 2 protostellar disks. So there's extra peaks here. But then thereafter, the ionization drops off. Then we see the PA emission in orange comes up right after the ionization front and then drops off. And then we see the H2 line emission. This is the vibrational line emission. And we see something kind of unexpected. We see 3 dissociation fronts, dissociation front 1, 2, and 3. So here's the overall picture that emerges. Here is the theta 1 OREC, and that creates a big ionized cavity. And that ionized cavity is eating its way into the Orion molecular cloud. And the PDR, we're looking down this way, the PDR is kind of the edge of this bowl. So we see a larger column density along the bar. And so this overall picture, it's been presented before, but now JWST gives this very detailed view of the very small scale structure of the Orion bar, the relative distances, the physical conditions in the gas, and AV towards various lines of sight. So here's just a few examples. Here's the ionization front. There's theta 1 OREC, and we get a UV field of 5 × 10⁴ incident on this ionization front. And we get that from analyzing the oxygen 1 lines, which at 1 micron are fluorescent lines. So they're pumped by the UV radiation field. They come back down, and we can get an estimate of the UV pumping field. We can get an estimate of the gas density. So here's the distance between the ionization front and the dissociation front. And we say that that's about an AV of 1. That gives you a density in the atomic gas between 5 to 10 times 10⁴. We also get an estimate of the gas and the warm molecular hydrogen by making these excitation diagrams. So this is the ratio of the column density in one of the levels divided by the statistical weight of the level versus the energy above ground of that level. And every single one of these are measured line intensities. And so these lower levels are collisionally excited. So you can fit a line through these lower points and you get a measure of the gas kinetic temperature. That's 670 degrees. You also get a temperature in these upper levels. These are UV pumped levels. That's not really a gas kinetic temperature, but it does tell you something about the excitation of these levels. You can also get a measure of the column density of warm H2 along a line of sight. So that's the excitation diagram for a typical point in the DF1, but we have diagrams for every single point in our near spec map. So we can get maps of the gas temperature and maps of the warm H2 column density. So what we hope to do then is to check the H2 formation rate in PDRs. Now I said that H2 forms on dust grains, and the rate in diffuse gas is pretty well known, and the process in diffuse gas is pretty well known. But in PDRs, the gas temperature is higher, the dust temperature is higher, and the exact same process won't work in PDRs. So we hope to be able to check the H2 formation process and see if we can understand it, see in more detail how it works in PDRs. We can also check the photoelectric heating rate in PDRs. So the heating rate that I gave before, that was really based on diffuse cloud observations. But in PDRs, the Paul abundance could be different, the distribution could be different, so the photoelectric heating rate might be different. And so this might be a way to really constrain the physics a little more. So here I've drawn DF1, DF2, DF3 as a series of little steps, as if it were kind of a geometrical effect. So here you would see the UV shines on these little stairs, and you'd see a layer of warm H2 at the front of every one of these stairs. And along the line of sight, then you'd see a peak of warm H2 emission. So that's kind of a geometrical interpretation of what's going on. We don't really know. That's just one idea. We also find from looking at carbon-1 recombination lines, we see very dense substructures in molecular gas, 10 to the 6 to 10 to the 6, a density of 10 to the 6. And that was suggested earlier. There's we see these high JCO lines from Herschel, so a much larger beam, but they also suggested there was a very high density, high pressure molecular gas. We see HCO plus, J equals 4 to 3 lines in AMA. So we see these high density, high pressure molecular clumps in this lower density environment. So we wonder how you can get those. So one interpretation is that there's dynamical compression of molecular clumps. So I said earlier that we saw photoevaporation of the neutral gas off the background molecular cloud at about 1 kilometer per second. So that means the neutral gas is advecting towards the ionization front through the PDR at 1 kilometer per second. Another way to look at that is that the ionization front is eating its way into the molecular cloud, and that sets up what's called a D-type ionization front. So what that means is it sweeps up a column density of gas, and that swept up column is really the PDR, and that column is then moving into the molecular cloud. So there's no shock over here. The shock is way down here as that swept up column moves into the cloud. So then the idea is that there's turbulent density fluctuations here. All of this behind the shock is compressed gas. And then these are these compressed pre-existing clumps that form the high density molecular clumps. So this dynamical picture of PDRs has been presented earlier, but there are some significant differences between what I just said and what was presented earlier. So the idea here is that dynamical PDRs might amplify those turbulent fluctuations and create these very high density clumps. So I have some conclusions. PDRs are regions where the FUV radiation plays a role in the heating or the chemistry. It includes many environments, clouds near massive stars, diffuse gas, protostellar disks, everything. Everything's a PDR. Then from observations of OH plus and H2O plus, along with PDR models and laboratory results, we try to constrain the cosmic ray ionization rate in diffuse gas to about 6 times 10 to the minus 16. That was for a density of 50. The rate scales as the cosmic ray rate over the density. We'll have to see how that might change for future measurements. The PDR lines can be used to measure the gas physical conditions and the kinematics. The stellar winds in H2 region, thermal expansion seems to dominate, at least in the sources that we studied. There's many small scale structures seen in JWST observations of the bar. The observations will greatly constrain the PDR physics, the heating rates, the H2 formation rates, but also some of the time-dependent effects due to advection and due to compression. Thank you.
So thank you very much for that very effort and informative and authoritative, above all, intelligent overview of PDRs. So as normal, I'll invite questions from the audience.
Barely, not through the microphone though. Go ahead. So let me see if I understand. You're asking about the two propylids? Oh, the Herbig-Haro objects. Yeah. Yeah, exactly right. So yeah, so there's a Herbig-Haro object there. It's very faint. It's hard to see, but it's definitely there. But yeah, it looks like it's just in the ionized gas.
That they were actually originated far away and they are actually impacting the PDR and therefore emitting a lot of O1, C1 emission, but it seems that they are not.
Right. It seems like they're not interacting much at all. And so maybe they're foreground. So that the role that, yeah, so right. Yeah, so that's true right here. So there's a really bright star there. It shows up a little bit better in, oh, there it is right there. It looks like it doesn't play a role because there's so much material here on this back side that it's effectively, the bar is effectively shielded from that theta 2 REA. And we've looked at that. You'd expect to see, illumination from both sides, but it doesn't look like that's the case. It looks like there's sufficient material around that star to shield the bar. Yeah. Yeah.
Okay, any more questions from the hall?
I was wondering whether, returning back to this issue of the driving of the bubble with the stellar winds versus the prediction of Lachlan-Lancaster's theoretical work. Their analytic model is a very good solution to their numerical simulations, but obviously these are idealized. So I wonder whether there are any features of driving these bubbles in a real environment that versus the idealized simulations that you think might explain this discrepancy.
So, well, I'm not really an expert in those kinds of hydrodynamic simulations, but someone said that it's due to the what is it called, where it's numerical. It's where processes from one cell kind of spread into the other cell, and so I forgot the term. Yeah, so really you have a sharp contact discontinuity between the bubble and the H2 region. But if that's not really resolved, it effectively kind of spreads the H2 region gas into the X-ray emitting gas as a numerical artifact. So that's one explanation. I really don't know. The only thing I can say is that for at least the bubbles that we find, they seem to behave as if the X-ray is dominating. There's X-ray, there's the pressure in the X-ray gas that's comparable to the pressure in the H2 emitting gas, and it's comparable to the pressures in the PDRs. And that's what you'd expect if the whole thing is driven from the inside.
Okay, thank you. If I may, I'd like to ask a question going back to could be less complicated. The observations of the diffuse clouds, the Neufeld observations of the cosmic ray, or the inferences about the cosmic ray ionization rate.
Right.
Could you remind us where those clouds are? I mean, they're all fairly local, aren't they?
No, they're all the way between here and the galactic center.
Is that really true? Oh,
Yeah,
that's interesting.
So, I mean, some of them are not that far away
Uh-huh.
because you know where the infrared background sources are. And so they can't be any farther away than the background source. But some of the background sources are pretty close to the galactic center.
Yeah, I mean, apologies if I've missed that in the papers, because I am familiar with the papers, but I mean, did you look to see, I mean, you've got about a factor of 10 in inferred cosmic ray ionization rate from the smallest to the largest.
Yeah.
Is there any correlation to galactic centric distance for those numbers?
Yeah, so we haven't done that. And that's really something we really need to do.
In
yeah.
principle, you could do it because you have
Yes.
a kinematic distance to the clouds, I presume.
Well, yeah. I mean, yeah. Exactly.
Okay, that really, really would be interesting.
Right.
Okay.
No, I agree.
I had a question about C1 because you didn't talk too much about C1 effect at the very end. From the PDR model, we sort of expect C1 to be an envelope around the molecular gas, but observationally, we don't seem to really see that.
Yeah.
So what can you say about it?
Yeah, so that is sort of a classic problem with C1 that, boy, as soon as they started observing C1, they said, well, this doesn't look like a kind of layered structure. What's going on? So there was a paper by Ralph Gleason and Simon Glover some time ago, and Clark, I don't know his first name, but if you look at a cloud as a whole, then it's not just a plain parallel thing. It's not like this onion skin thing. It's turbulent, and there's various ways in which the UV field can penetrate. So that's one of the ideas. The UV field can kind of penetrate and dissociate some of the CO, and you end up getting kind of this intercloud carbon one that comes from everywhere. And what might be what's going on.
Thank you.
Okay, well, I don't see any more questions at the moment. Great. Oh, that's really an evening to look forward to. Thank you very much again. Thank you very much for this very authoritative,
Thanks for having me here.
informative talk. Thank you very much, Mark.